Okay, folks, Unit 5 progress check. I think I can do this all in one 15-minute swoop. We will see if I go too fast. I know that sounds weird because you can pause, but if I'm too abrupt, please email me and let me know if I'm not being as detailed as I need to be. Okay, so this is questions A and B. When we're looking through this from the very beginning, we need to know twice differential means that it's differentiable in the original function, the first derivative, and the second derivative. They give us f prime of 1 is equal to 0, and the second derivative is given by that function right there, from -1 to 3. Now, this is not, obviously, they don't have calculator problems for our situation, but anytime they give you an interval like this specifically, and it's a calculator, you're putting this in your calculator. Again, you're always in radian mode, and you're restricting your x window to -1 to 3. You are not giving anything else, because that's what you want to look at specifically. And on what open intervals is this graph concave up? All we do is we put it into our calculator, our window, we graphing window we just talked about, and we're looking for where it's above the x-axis. All right, and then we identify those intervals by calculating zeros and stuff like that. So that's that. Okay, simple enough, straightforward. Number 2, does f have a relative minimum or a relative maximum at, or neither, at x equals 1? Justify your answer. Well, we're talking about a relative minimum, relative maximum, but we don't have the original function derivative. We only have the second derivative. So what we do is we understand that the first derivative is 0, and then we calculate the second derivative at 1 simply by using our calculator, and we find out that, and we're just evaluating it. Remember, we're given the second derivative. We find out that it's -0.54. We don't really care the value. All we care about is that it's less than 0. Okay? And what that means is it is concave down at that location. So by the second derivative test, you need to say the phrasing second derivative test, there's a relative max at +1, because we know f prime at that value is 0, and we know f double prime at that 0 is less than 0. Therefore, it's concave down, and it looks like this. So that makes it a maximum. Okay. Part C is a little more involved. Use the mean value theorem on the closed interval to show that f prime of -1 cannot equal 2.5. So what we need to do here is we need to, if we're saying it can't equal 2.5, then we're actually going to try to assume that it is 2.5. All right, and go from there. So what that means is we first set it equal to 2.5. We then find the average rate of change. We're talking about f prime here. So we go f prime of 1, which we know to be 0. They gave that to us. F prime of -1, we're assuming to be 2.5. We're finding the difference, and then we're finding the change in x, which is 1 minus a -1. So we end up with, if in fact f prime of -1 was 2.5, then our average rate of change was -1.25. All right? And then we have to make sure that we do this because we're talking about the mean value theorem. So f prime is continuous and differentiable. It's continuous on the closed interval, -1 to 1, and differentiable on the open interval, -1 to 1. And by the mean value theorem, there must be a c on this interval. So f double prime is equal to -1.25. So again, our average rate of change, if in fact this were 2.5, would be -1.25. So what we're saying is there must be some situation where f double prime is equal to -1.25. But if we look closely at this function, and remember, we're restricted to -1 to 1, this function will never get beyond -1 to 1, because we know that cosine's range is -1 to 1, because our value of a is singular at this point. We know x squared from -1 to 1 will never get bigger than 1 or -1. Therefore, we know this whole function can never reach, and it can never go beyond -1 to 1. Therefore, there is no such c where f prime of -1 equals 2.5. All right? So again, we assume from the very beginning that it equals 2.5, and then we appropriately move forward using average rate of change. And then from there, this is going to take a little bit of common sense or a little bit of figuring it out. But that we understand that graph can never go beyond -1 or 1. Okay, I'm going to pause for a second and let you see if that makes sense. Okay, part D of number 13 is, does f have a point of inflection at x is equal to 0? Therefore, we want to see if f double prime changes sign. Not that it's equal to 0, but that if it changes sign at that point. And because it doesn't change its sign at 0, then there is no point of inflection. And again, we do this just by the calculator. We don't overthink it or anything. We just go right by the calculator. All right, so that's number 13, A, B, C, and D. Okay, number 14 gives us this graph of G, right? And it asks, it said from -3 to 3, we know that. And it's twice differentiable as before, except at 0, and that's okay. And then they tell us the initial value, so f of 0 is -1, and then they give us the derivative of f. So this is the initial value, all right? And the first question, part A, is find the x-coordinate of each critical point of f. Classify each critical point as a location of min, relative max, or neither. Justify your answers. Okay, so the first thing we need to make sense of is this statement right here. Sign charts are not sufficient by themselves as justification. That does not mean we don't use a sign chart. It just means we can use a sign chart to make understanding of it for ourselves. We just need to use different notation and different explanation after the fact. So critical points are when it equals 0 or undefined. Our derivative is right here. This will happen. I predict where you're going to have e to the x at some point. E to the x is never 0, and it's always positive. So we don't concern ourselves with that as far as the 0 goes. We set this equal to 0, and we end up x is equal to plus or minus root 5. Taking the square root. Okay, we don't really know what the value of plus or minus root 5 is. We do know it's bigger than 2, or I'm sorry, bigger than 1. And we do know it's, it's not very, not much bigger, so we can go to something like -3 and 3 for our test values. And in between, negative root 5 over 2 and positive root 5 is 0. All right? So we just plug these values into our derivative function, remember. So we're going to plug a test value of -3 into this value. We discount the e to the x, it's always positive. Therefore, this becomes a positive times a positive, and this is positive. We plug in 0 here, we get positive times negative, therefore this is a negative, and lastly we plug in 3 to this, and we get a positive times a positive, so it's positive. So our graph looks like this, up, down, down, up, all right? Again, this is not sufficient. We can't just leave it like this and say maximum and minimum, so we need to say f has a relative maximum at negative root 5 over 2, because f prime changes from positive to negative. And we do the same thing for the next part. F has a relative minimum at positive root 5 over 2 because f prime changes from a negative to a positive. Use your full sentence here. This is just for your abbreviated version. Okay? Again, this makes sense to us, but we need to put it into words. We can't leave it just like this. Okay? Part B, find all values where the graph has a point of inflection. Give reasons for your answers. So from here, we're looking at the very start, we need the second derivative to be equal to 0. We have our first derivative already, so we take the second derivative using the product rule. So the derivative of the first, which is the derivative of this, is 2x, normal second, plus the derivative of the second, which is e to the x, is simply e to the x, times normal first. At this stage, and always and forever, we're going to be making this move. We pull out an e to the x because there's a common term, and we have this left inside. We want to know when this is equal to 0. We can't factor this. We could maybe with some serious guess and check, but we're instead just going to use the quadratic formula, and it works out really nicely. So this is a non-calculated question, so this is going to work out nicely. So we have our -2 plus or minus root 9 over 2. That means -2 plus 3 over 2 and -2 minus 3 over 2. And we get 1/2 and -5 over 2. In this case, it changes signs in both cases. So in both instances, it changes sign. So these are both points of inflection. Okay, for part C and D, I'm going to go right to the answer key. Fill in the missing entries in the table to describe G prime and G double prime on the interval. In this case, we're looking back at our graph. So we're looking back at our graph, and we're recognizing that from -3 to 0, this graph has a positive slope. It's going upward. From 0 to 3, it also has a positive slope. Again, it's going upward. And this is really about the second derivative. The first derivative is really straightforward. Positive second derivative because it's concave up on that interval, and negative from 0 to 3 because it's concave down. So that's a really nice answer, really nice problem. We can get that pretty straightforward. Okay. The reasons for your answer is exactly that. It increases from left to right for the G prime. These are self-explanatory. I think you can get those yourselves. If not, email me. So let h be the function defined here. So right here we know we're going to be using the product rule. Is h increasing or decreasing at 0? Give reasons. So we take the derivative, and we're using the product rule. So we have the derivative of the first. I'll get a little closer. Okay, so the derivative of the first is f prime normal second g plus g prime f. So there's my product rule. You do not necessarily use this. You can go right to here if you want. F prime of 0 times g of 0 plus f of 0 times g prime of 0. All of this can be determined by the graph and the function. So we don't even need to have factored form here. So we know that e to the 0 is 1. So f prime of 0 is going to be negative because we have a 0 plugged in there. And then f of 0, they already told us, is negative 1. And then g and g prime of 0, we're talking about the graph. We're talking about referring to this. So here it says f of 0 is less than 0. We know that. F prime of 0 is less than 0. We know that. G of 0, remember it's 2, so it's greater than 0. And g prime of 0, because it's going up, is also greater than 0. So then from here, we can just very easily see that the entire function is negative, and h is therefore decreasing. You have to put the part where h is decreasing on the interval, or at 0, I'm sorry.